Welcome friends. Today we will explain about carbanion and its resonance stabilization. So I am Tanmay. So let's start the video. So this carbanion is an electron-rich species. You can see because of less electronegativity of carbon, this carbanion is more reactive and it is a very unstable reaction intermediate. I have explained this thing in my previous video, so if you haven't seen, I suggest you to see my first part of this carbanion, which is a continuation of this study. So it needs electron withdrawing group, and electron withdrawing group could operate from using minus I and minus R. Okay, minus I means inductive effect. I have explained in my first video, and right now we are going to describe mainly about minus R means resonance withdrawing. How resonance withdrawing means, if we consider, it will have a vacant p orbital which will drag this electron density, and this electron density will be dispersed and the carbanion will be stabilized. So this is the basic concept. Okay. So now how can we achieve this? Means how withdrawing could be achieved, electron withdrawing. This electron withdrawing or stabilization of carbocation could be achieved by conjugation with multiple bonds. Conjugation with multiple bonds or atoms like heteroatoms. Okay. So let's start. So first part we will explain about conjugation with the multiple bonds. What does it mean? Conjugation of the multiple bond, what do I mean? That for example it is a carbanion minus. It could be double bond, it could be triple bond, carbanion, let's consider R, and like that. Okay, so let's explain this part. Okay, another could be heteroatom. I'll come this part later on. So let's explain about this. So if we consider the resonance stabilization, this is allylic, means this, and this is acidity. So this, and another let's draw about benzylic. This. So how this allylic? This is resonance means it delocalizes electron density in this way to form double bond this. And you can see these are equivalent canonical structures, so it is stable. Second, how it can delocalize its electron density in this way. This is will push and this will come here. This. So in this way, acid means alkynyl. And this is vinyl. This is benzylic. How it stabilizes? It pushes electron density. It goes up. So what it results? Electron density come here. This is this. Sorry, I made a mistake. Mistake means it should not be like that. This bond will come. So this is negative charge will come here. So in this way, and another thing, negative charge can further come here. In this way, another 3 canonical structure are possible. So this indicates how this carbanion is stabilized through resonance. And if we check the order, this benzylic is more stable than the allylic. Okay. So this is the stability using this carbon-based skeleton. Now we will check whether the attachment of multiple bond means other, how it stabilizes. For example, if we consider heteroatoms, other heteroatoms like this carbanion is attached to oxygen. Okay, so if we do oxygen, heteroatom generally what do we mean? Carbon, nitrogen, oxygen, or you can say halogens. Okay, so if it is attached to oxygen, then what happened? Actually, these oxy-carbonyl attachment could be different functional groups, like this is simple if R equal to aldehyde, or if R equal to H, that is aldehyde, and if it is R equal to any alkyl group or aryl group, that is ketone. So ketone. Second, it could be ester, for example ET. Even this could be, okay, another different ester, that is anhydride minus here. This is anhydride. Or we can say, if this is nitrogen, then negative charge is here, that is nitride. Okay. So these groups can, and in case of halogen it's little special, I'll explain later. So this is how it stabilizes. This donates and the density goes up. So double bond O minus and R. So in this way, due to this resonance is delocalizes. Similar way, this carbonyl stabilizes. In case of nitride, how it stabilizes? Electron density goes and one bond open up, like simple. That is triple bond. CC triple bond. Its stabilization is like CC triple bond. So this is carbon, and in case of here it is a CH triple bond. So in this way, resonance helps to stabilize. So this is the role of heteroatom. Okay. Another type of, and another thing you can find out such type of intermediate produced. This is during aldol. This is Claisen ester condensation. Okay, this is similar. Even this is this could be a similar type of aldol reaction. Even like this, another heteroatom type could be like nitromethane. This thing, how this nitro group stabilizes? Actually, nitro group stabilizes via condensation. How this nitro group actually this. What happens? It provides electron density, it opens up. In this way, this nitro group is also stabilizes the carbon. And like this nitromethane, its parent compound, it's acidic enough. Okay, this is acidic enough that it can. So this is the real proof that this nitromethane can stabilize this carbon. Okay. So similar like this, there are another type of conjugation possible, that is conjugation with heteroatom. Heteroatom means like sulfur and phosphorus. How? If we consider this DMSO molecule, dimethyl sulfoxide, it can generate an anion here. Okay? Okay. So it can generate an anion here, and this could be stabilized by the conjugation like this and this. So CH2 and this is. So in this way, this molecule could be stabilized. This is one another. Another way, phosphorus, how it can stabilize. For example, phosphorus to attach carbon. Let's consider CH3. If it is attached with triphenyl phosphine and this, then it can stabilize in this way, forming a double bond. How this can form? Nitrogen can't, because phosphorus can expand its coordination, its valency, because of the participation of energetically accessible d orbital, and it can become pentavalent. So this is, and you know, this is one of the very famous reagent, that is Wittig reagent. Okay, so this intermediate is utilized in Wittig reagent, and in Wittig this is the actual intermediate which reacts with carbonyl compounds to produce double bond. So in this way, these ylides, this material can, this conjugation can stabilize the carbon. Second, what could be the other? So up to this, we have explained that conjugation with the multiple bond, minus I, minus R, this, and another type of material are there which can stabilize the carbon very easily, or generate them very easily. That is that is active methylene compounds. Okay, let's clean this part. That is active methylene compound. I will make a dedicated video on this later on. Active methylene compounds. What they do? Actually, active methylene compound means it's a methylene group attached to two electron withdrawing groups. Electron withdrawing groups. In reality, what? Like carbonyl group. So, simplest example, let's take methyl. This is called acetyl acetone, or in short ACAC. Okay. So this is acetyl acetone. What happens? This proton easily abstracted by this, and it generates this carbanion. Okay, and this carbanion is highly stabilized by conjugation with this side. So what will it look like? Minus charge here, this and this double bond. Similarly, it can be resonance stabilized by conjugation with this. So what will be the minus charge will come on this, and this is the zero bond. So in this way, this active methylene compounds can stabilize, and there are many active methylene compounds reported. For example, like many other active methylene compounds, like this is acetyl acetone, ethyl acetoacetate. This is ethyl acetoacetate. Okay. So EAA, this is called EAA, diethyl malonate. What does it mean? This is malonate. This is malonic acid. If we take OH, both, this is malonic acid. But if this OH prepare a star like OET, this is diethyl malonate. Okay? So it is called DEM, diethyl malonate. Even another material, that is di-cyanomethyl. What? CNC. If we write better, it will be easier for you to understand. This is. So what happens? This abstracts electron density. This group withdraw electron density and stabilize through resonance. And if we check the actual electron withdrawing capability, this is number 1 among this listed 1. This is 2 acetyl acetone ACAC. This is 2. This is 3, and this is 4th. Okay, this is their reactivity. Because two very highly electron withdrawing groups, cyano, so it's very strong withdrawing. That's why it is proton releases easily among all four. So one question MCQ could be given to you. This is second is this because 2 carbonyl. Third is this because 1 carbonyl, 1 ester, because ester has 1 cross conjugation here, and this bond will go. And here 2 cross conjugation, so this is the order. So please keep this thing in mind. It could be given a MCQ that among 4 active methylene compound, which is the most active, or another sense it could be given that arrange themselves in order to their acidity or proton donation capability, like that. So this is about the active methylene compound. Now I will explain about some halogenics. So in my last video, I have given an explanation. So I suggest you please see that. I will give just a very quick explanation. For example, this CCl3 minus. This is a minus. CCl3, CF3 minus, and we will compare this with CCN3 because Cn is also electron withdrawing, so CCN3 minus. So these 3 examples we will discuss. So first, if we check the pKa value, the pKa value of this material means this it's generated from corresponding HCF3 fluoroform. This is from chloroform HCCl3, and this is generated from cyanoform HCCN thrice. If we check the pK, its pK around 25 to 28 pK. Okay, its pK around 16, and its pK around -5. This is the point to be mentioned. Focus. How? This is due to the -I effect of 3 fluorine atom. This HC bond became more polar, that's why polarizes, and it stabilizes only using -I effect. This thing -I is there, chlorine, but along with -R. So -I and -R, both effects are possible. Third is -I and -R. How? I have explained about how this nitromethane example, this electron density comes this and it goes swing this way. But the point to keep in mind that this is, in spite of having maximum electronegative atom, this is having 25. This is 16 because it donates electron density to the vacant d orbital of chlorine. I have explained in my first video. You can have details idea. But most important part is this. How? Actually, this abstracts electron density so efficiently that it produces this anion, and its pK value is in minus, and minus pKa value indicates the strong acids. Okay, keep it in mind, minus pKa value is for the strong acid. Even if we consider this paratoluene sulfonic acid, you know, you have used a lot of this reagent. This is like this. This is paratoluene sulfonic acid. If we write properly, it looks like this paratoluene. In short, it is also called PTSA. Why I am giving example? It is a sulfonic acid, so easily donates its electron. And what forms? O minus and H plus. Okay? And this negative charge is delocalized using these 2 sulfur with different canonical forms, and this negative charge delocalization produces 3 canonical structure, 3 equivalent canonical structure, and its pKa, that is the most fascinating thing, its pKa. So now you compare this versus this. So just think again that its acidity is so much, it's comparable with this pKa of a sulfonic acid, paratoluene sulfonic acid, and this is the most interesting thing. Its pKa -1, it's -5. So this is more stronger acid than this, and how this? Because of the stability of carbocation. So what message I want to give? This if delocalization possible in extreme extent, then this carbanion could be a stable species. And what acid means? Acid means, if we consider acid, Ha means acid forms an equilibrium, that H plus E minus, and the acidity depends on the stabilization as of this proton as well as this, and this is the acid and this is the conjugate base Cb. If the conjugate base is stable, then protonized means acid's ionization is faster, and conjugate base, we say that carbon ion, carbon negative is reactive intermediate, unstable, everything is true, but if proper condition could be provided to them, then it will be a very, very stable molecule, this conjugate base, and that's why it's pKa 5. You may have one question, you may ask that, okay, since we say it's a tricyanomethane, it could be a bulky molecule, that's why it is not stable. Okay, you can say that question, because, or you can argue this with this tertiary butyl. Okay, this tertiary butyl, this versus this. So you can think this, why bulkness is not that much important factor. If you check these 2 examples, this tertiary butane versus or 2-methyl propane versus this. Here CH3 looks like this, hydrogen, and Cn looks like it's a needle shape, one direction. So it is less bulky than this. So that bulkiness logic is not perfect here. Here the most important thing, the electron withdrawing effect of this cyano using minus I and minus R, which stabilizes this. So this is the end of this video, and next video I will explain carbocation stability through resonance. Means this is also resonance, mainly through aromatic stabilization. Aromatic stabilization is the maximum. So we will discuss in next way how aromaticity stabilizes carbon ions. So thank you everyone for listening my video. So if you like my videos, please give a thumbs up and share this video with your friends and subscribe my channel Chemistry, the Mystery of Molecules, and please press the bell icon so that you can get the notification of every single video I upload. So goodbye, stay blessed.